Welcome to the third and final part in the series on support vector machines and kernels. In this section, we talk about kernels, which are a general concept and can be used with many different methods. However, they are often used together with support vector machines, which is the reason why we discuss them in this context. Let's start by recalling that the only thing we did so far in previous lectures on linear classification and in this lecture on support vector machines is that we've constructed linear classifiers. That means we construct a classifier which is a hyperplane that separates the data into two halves. All of the data points on one side of the hyperplane are classified as class 1, and all of the data points on the other side of the hyperplane are classified as class -1. However, often the dataset is not really linearly separable, which means we cannot even find a hyperplane that will neatly separate the two classes. And in the cases of hard margin SVM, if you specify the optimization problem, you will not be able to solve it because most of the constraints or some of the constraints will be violated. And one thing we did was to say, okay, we will now relax these constraints and create the soft margin SVM. And in this case, you can really plug in any dataset and you'll get out a solution. But if you think about it, let's see what happens if you run soft margin SVM on the example shown on the slides. Then we will get some solution, but this solution will not do a good job because the classifier will not be able to accurately separate the two classes. So no matter which hyperplane we choose here, there will always be a significant number of mistakes because we can't really separate the blue from the red with just a simple line. And this is because the data in this case is fundamentally non-linearly related, so we cannot really separate it with a linear decision boundary. And one thing we realized that we can do even before, which we've discussed in some of the previous lectures, is that we can use basis functions. A basis function is simply a function which transforms the input features from one space to a different space. So it's really just a function which takes in as input a vector which corresponds to the features of a given instance and outputs a different vector which could be even of a different dimensionality or it could even be a scalar which corresponds to the transformed features in the new space. So let's see how this looks like. Let's say we're given data which has two features, x and y, or x1 and x2, and then we apply the following transformation. Here we keep the first two coordinates, so the first two features stay the same as our input, but then we add one additional feature which corresponds to this expression. And because in this case we are working, we're going from 2D to 3D, we can visualize these two spaces. So data started out like this, and then after the transformation, after we apply phi of xi, we obtain this feature space. So now, instead of computing the hyperplane in the original feature space, we simply create a classifier in the new feature space. That is, now our classifier is just sine of W transposed phi of xi plus b. So before we just had W transposed xi plus b, but now first we apply this feature transformation and then we do the classification in the new feature space. And now we see that the classifier is still linear, but it's now linear in this new feature space. And the way we can imagine that is that in this new feature space, essentially we have a hyperplane, which we can draw something like this. And the weight vector W, as always, is normal to the hyperplane. Right, so what you can do now to see what kind of decision boundary corresponds, this linear hyperplane corresponds in the original feature space, is you can look at all of the data points that lie on this hyperplane. So these are all of the data points for which W transposed phi of xi plus b equals 0, because that's the definition of the hyperplane, and then take all of these points and map them back to their position in the original feature space. And if we do this, the decision boundary will look something like this. so these two essentially are the same. So this is our decision boundary. And even though the classifier is still linear in the new feature space, with the help of the basis function, we obtained a non-linear decision boundary in the original input space. And this case, in this case, this helps us to perfectly separate the two classes. Okay, so how could we now use these feature transformations phi when we work with SVMs? Well, it's actually pretty simple. If you recall how the dual formulation looked like, so we were trying to maximize the dual function g of alpha, and the only place where the features xi and xj show up is in this part of the objective function. And the only way they show up is as the inner product. So we have xi transposed xj. So then the simple way to include the basis functions is, instead of using xi, xj, we simply use phi of xi transposed phi of xj. And doing this with kernelized support vector machines, and this supports now the option of having a nonlinear decision boundary in the original input space. But this is not yet the kernel trick. This comes next. Basically what we can do is we can say, well, instead of writing out this feature product, the product between phi of xi transposed and phi of xj, let's call this, let's say that this is a new function. So we call this function k. It's the kernel function. It depends on the features of the data as instance I and the instance j, and we simply define it as phi of xi transposed and phi of xj. And now in the dual, instead of writing out the inner product, we simply plug in this function k. This very simple idea of using the kernel function directly instead of using the basis functions phi is already called the kernel trick. So here, one thing to keep track of is that the kernel function takes in two inputs and outputs a scalar, but the basis function takes in a vector and outputs another vector. So just keep in mind what is the input and output of these different functions. And this kernel trick is actually widely used, not only with SVMs, it can be used with linear regression, k-nearest neighbors, and when we do this, we obtain what are called the kernelized variants of linear regression or kernelized k-nearest neighbors and so on. In one of the next lectures, we'll talk about principled component analysis, which can also be kernelized. So many of the methods in machine learning, the machine learning literature can actually be kernelized. But at this point, you might be thinking, what's the point? Why did we really go through this trouble of defining this new function? And why can't we just use directly the basis function phi? Well, the thing to realize is that the kernel function, we can view it more generally as measuring the similarity between two inputs. So we can think of k, the function k, as taking two vectors, in this case xi and xj, and outputs a single number. And if this number is high, then xi is similar to xj, and if this number is low, xi is dissimilar from xj. And once you've realized that the kernel function basically measures similarity, you can plug inside of this function different objects which are not necessarily vectors. So for example, you can define it, for example, that the kernel between a lemon and an orange is 10, and the kernel between an apple and orange is -5, or any arbitrary numbers. So in some sense, if you have access to a function in which you can plug in two objects, and this function returns a number, a single scalar, which tells you how similar they are, then you don't really need to know what the feature transformation is. And this might be useful because let's say we have the kernel between two graphs. So this is one graph. So this is an object which has nodes and edges, and some different graph. So these two objects, we might want to do machine learning with these objects. We might want to classify these graphs from from these kinds of graphs, but we can't really easily represent them as vectors. There is no numbers, there is no fixed dimensional representation that we can obtain for these graphs inside here. But if we can specify a kernel function somehow, it doesn't matter how, which takes two graphs and outputs a single number, then we can basically do support vector machines on graphs. Or similarly, if the input is not graph but it's text, we can plug in two sentences, and the sentences can be even of different length. And as long as we have a kernel function which can output how similar these two sentences are, think of it, maybe this kernel function comes from some different model, from some different analysis. As long as we can do this, then we can apply support vector machines and train a classifier. And then the other point why kernel functions might be useful is because some kernels, some functions actually correspond to a dot product in an infinite dimensional feature space. So if you kind of write down the corresponding phi of xi and transposed phi of xj, the phi will map from a finite dimensional space to an infinite dimensional space. And in this case, we won't be able to even compute it, right? The basis function is an infinite dimensional space. We can't really compute it. But if we have the kernel function, we can just plug the two objects in, and outside we get how similar they are. Okay, so now let's see what happens if we use different kernel functions. If we specify this kernel function, so we have that the kernel function of a and b, you plug in a and b and you spit out a transpose b. So this is the linear kernel, or in other words, we have not used any kernel because this dot product is the same thing that we had in the original SVM variant. We see that the decision boundary is again just a line. It's just a hyperplane in the original input space. Alternatively, if we used a second order polynomial kernel such as this one, so the function of a and b is a transpose b squared, we see that the decision boundary changes. So now we have this curved decision, or this nonlinear decision boundary in the input space. And in both of these cases, we can write down what is the feature transformation that corresponds to this kernel. So in this case, phi of a is just a, so there is no transformation, and this is equal to phi of a transposed phi of b. And similarly, in this case, we can write out what the corresponding phi of a and phi of b is. Okay, but then the question is, can we really specify any function? Can we really choose any k which takes into inputs and outputs a number, and will this give us a valid kernel? Unfortunately, no. So this is not really true, and this function k has to satisfy certain conditions in order for it to qualify as a kernel. And there's two ways to think about it. One way is that if you can write down the function as a dot product in some feature space, or at least if you can prove that your function k of a and b can be written down as phi of a transposed phi of b, even though this phi of a transpose is maybe infinitely dimensional, or it's complex, or it's some crazy object, if you can prove that this thing really holds, then you know that it's a valid kernel. You know that k is a valid kernel. Here you don't have to explicitly compute it this way, but if you can show this holds, it's enough. The other way to show it is via Mercer's theorem. And the idea behind Mercer's theorem is to form the kernel matrix, which is also known as the gram matrix, and show that this matrix is symmetric and positive semi-definite. And the way this matrix works is that you take in a sequence of data points, x1, x2 to xn, and then you compute the kernel between any pair. So here we have x1 and x1, x1 and x2, all the way up to x1 and xn. x2 to x1, and so on. So basically you look at the similarity between any data point and any other data point. And you take all of these numbers, which come out of the kernel function, and you plug them into this matrix, and you call this the kernel matrix. And now if this kernel matrix is symmetric and positive semi-definite for any potential data set, for any sequence of x1 to xn potential inputs, then we know that we have a valid kernel. So here be careful. It's not enough to show that only for a fixed number of data points, for like 10 data points. You have to show that this holds for 10, for 11, for 12, for any finite number of data points. So as long as you can show this, then we know that the kernel is valid. Then another question that might come up here is, what happens if we don't use a valid kernel? Let's say we just plug in any function, solve the resulting optimization problem. Maybe we solve it with gradient descent in the hinge loss formulation. Will this thing still work? Well, it might work in practice, but the optimization problem which you get is no longer convex. So the convexity of the optimization problem is tied to having essentially a valid kernel, or to having a positive semi-definite gram matrix. Okay, so how do we know then that a kernel is valid? How do we check? Because this condition might be difficult to prove in practice. Well, one idea which we can do is to apply kernel preserving operations on some basis of functions which are already known that they are kernel preserving. So you can think back maybe to our discussion of convexity, where we knew that certain functions are convex, and then applying certain operations preserves convexity. Something similar is happening here, where we know that certain functions are kernels, and then applying some operations we get again a kernel. So we know that adding two kernels gives us a kernels, multiplying a kernel by a positive constant gives us gives us again a kernel, multiplying the scalars, so two kernels, gives us again a kernel, and so on. So we have all of these operations which can be used to prove that a new function is a kernel. And I think this is what you will do in one of the homeworks. Now let's look at a couple of kernel functions which are often used in practice. The polynomial kernel is one such function, and we already saw one example of this earlier where we used a second order polynomial. But more generally, you can use any order polynomial, or in this case we have a transpose b to the power of p, which is a p order polynomial. We can even add an additional bias term, and this will still yield a valid kernel. The Gaussian kernel is actually one of the most commonly used kernels, and this is one of the cases in which this kernel actually corresponds to a dot product in an infinite dimensional feature space. So we're not going to go through the details of proving this here, but basically what you can think of is that the exponential function e of x, if you take the Taylor series expansion of e of x, you can show that this is 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus so on until essentially infinity. So this is like an infinite series, and because of this property of the exponential function, you can use this to show that the corresponding feature transformation for the Gaussian kernel is actually infinite dimensional, and then we have a dot product in this infinite dimensional feature space. So one thing to note about the Gaussian kernel is that the similarity between two data points A and B depends on the distance between them. So if two data points are very close to each other, then this is a small number, which gives us a high similarity overall. But the other thing is that we also have a hyperparameter, such as this sigma, which gives us additional control. So if we use a very small sigma, then we will only consider points close in our neighborhood as similar. And if we have a large sigma, then the neighborhood of similar points will be larger. Some other functions which are commonly used in the literature is this sigmoid kernel, which is actually not a kernel because the corresponding gram matrix is not PSD, but nonetheless people use it in practice because it seems to work well. In general, we might have these different hyperparameters like the value of p in the polynomial kernel, or the value of sigma in the Gaussian kernel, or these values in the sigmoid kernel. And depending on how we choose, first of all, which kernel we use, and then which hyperparameters we use, we're going to get different kind of behavior. So the decision boundary will look different. And because the Gaussian kernel is so popular, let's quickly look at one example of how this looks like in practice. So in this case, we're showing a data set which has two classes, as always. The red data points belong to class 1, and the blue data points belong to class -1. And we've trained a support vector machine where we use the Gaussian kernel with different values of sigma. And then we see what happens as we change the value of this hyperparameter sigma. Well, overall, what we see in all these pictures is that the Gaussian kernel was able to adapt to the shape of the data. So we see that the two classes are in this sort of spiral shape, and then the decision boundary takes on the same shape. So we see that all of the data points which are in this region will be classified as class 1, and all of the data points which end up in this other region will be classified as class -1. And then the other thing we see here on this example is that the smaller the value of sigma, the more fine-grained the decision boundary is. So if you look at the decision boundary over here, we see we have many more wiggles, and the decision boundary is much more fine-grained compared to this example where we have a smoother decision boundary. This ability of the Gaussian kernel to adapt the decision boundary to the shape of the data might not be a good idea in general. So let's see one example. Let's say we have two-dimensional data set, and we have data points that belong to class +1, and we also have some other data points that belong to class -1. But let's say that this data set is noisy, so we have also a couple of data points from -1 over here. So what's going to happen if we train a Gaussian, an SVM with a Gaussian kernel and an appropriately chosen value of sigma? The decision boundary will completely adapt to the training data, and it will perfectly classify all of the instances. So all of these data points will be classified as class -1, and all of these other data points will be classified as class +1. But this is we might not really want this in practice, because this part of the decision boundary, we've let it be influenced by something which is noisy, and now if a new data point comes in here, I think we would much rather have it classified as blue rather than green, based on what we observe around it. So if we're not careful with the Gaussian kernel, we might run into an overfitting issue where we fit all of the noise into the data. So then, as always, the solution when we have to choose such hyperparameters, and in order to avoid running into an overfitting issue, is we should basically just do cross-validation. The idea basically is that we take the training data and we split it into training, validation, and test set. We leave out the test set for the end. We don't touch it until we've found the hyperparameters, and then we simply train the classifier on the training set and evaluate it on the validation set. And then we repeat this for all possible values of the hyperparameters, or for a randomly chosen subset of the hyperparameters. For example, we might care about how to choose this penalty parameter c, which we had in the dual formulation, or we might care about how we choose the value of sigma or some other hyperparameter, depending on how our kernel looks like. So we evaluate the performance on the validation set for all of these combinations of hyperparameters, and then we simply choose the one that performs the best, the one which gives us highest accuracy. Finally, let's discuss for completeness how we actually classify a new data point with the kernelized SVM approach. So as before, it holds that the optimal weight vector is a linear combination of the data points. So W is simply sum over all I, alpha I, yi, and now we use the features but transformed by the basis function phi xi. And as before, only those data points which have a non-zero Lagrange multiplier, a non-zero value of alpha I, only those will contribute a term to this sum, which means only those will affect the decision boundary. And similar to before, we can use the complementary slackness condition, which basically stated that alpha I star fi of theta star has to equal to 0, and then we can just simply find one example where alpha I is non-zero, which means that fi of theta star has to be 0, and then expanding this term, we can we get exactly this expression from where we can solve for the bias. Then a new data point. In order to classify it, we simply remember only those data points which are support vectors, only those data points for which alpha I is non-zero, or in our case is even bounded between 0 and c. And we simply compute the similarity between the input test point x and these support vectors xj, the similarity as measured by the kernel, multiplied by alpha j and yj in addition to the bias. If you remember how this decision will look like before, it was very similar, but before, instead of this term, here we just had xj transposed x. But now the similarity is measured by the kernel function. One interesting thing we can notice when the kernelized SVM is written in this final form is that this classifier seems to behave as a newest neighbor classifier, where the distance to the neighbors is measured in terms of this kernel function. Let me tell you what I mean exactly by this. So let's say we have some one-dimensional data set where we have here some data points which belong to class 1, and then we have some additional data points which belong to class -1. And now let's say we plug in a new data set, a new data point, and we try to classify this one. So what we're going to do is we're going to look at the distance between this data point and all of the support vectors. Let's say this one is our support vector, this one is our support vector, this one, and this one. So we're going to compute the distance, or the similarity actually, between this data point and the support vectors. And based on this similarity, we're going to form this weighted average, basically. And let's say, for example, that the kernel function is the Gaussian kernel. In this case, if you look at the definition of the Gaussian kernel again, if the 2 points are close to each other, then the similarity is high, and if the 2 points are far from each other, the similarity is low. So the similarity, when we compute with the Gaussian kernel between this data point and these two data points, it will be very low, which means that the kernel will output a very small number, and they will not contribute that much to this sum. While with these two data points, because they are closer, the Gaussian kernel will output a larger number, which means they will contribute more to this sum. So then we have, so in the sum we will have, let's say, two large numbers, like plus 10, and then we'll have two small numbers, -1 and -3, where here the signs come from yj, positive class, negative class, and also let's say we have some alphas here, which I'm not going to write down, but basically the total sum will be positive, so then this data point will be classified as positive. So if you look at it from this way, basically this classifier behaves just as a nearest neighbor weighted classifier. Of course, we also have the bias, which has additional effects, but the overall structure is clearly like a nearest neighbor classifier or weighted nearest neighbor classifier. Okay, so now we've discussed almost everything about support vector machines. Finally, I want to talk about briefly some of the issues that we have with support vector machines. And one of the most prominent one is that it's really not easy to handle scenarios in which we have more than two classes. So for the entirety of this lecture, we were discussing the binary classification setting, where we only distinguish between two classes. But if we have more than two classes, it becomes a bit difficult. Still, there are some strategies you can use, and people sometimes use them in practice, and those are the one versus rest and one versus one strategy. So the way the one versus rest strategy works is that you train C classifiers if you have C classes, and in each of these you're trying to predict whether the data point belongs to class 1 or the rest of the classes. So let's write it down. So you have one classifier where you're trying to predict class 1 or the rest, and then you have some decision boundary. And then in the other classifier, again, you're trying to predict class 2 or the rest, class 3 or the rest. And now let's say we have a new data point. You plug this in, you plug this data point in, and let's say it lands on this side of the decision boundary, on this side of the decision boundary, and on this side of the decision boundary. So we see that in this case, the classifier reported rest, so we can ignore it. But here it says it's class 1, and here it also says it is class 3. So which one of these two do we choose? And the rule that people use is that we should choose the class where the distance to the margin is larger. So in this case, the distance to the margin for class 3 is larger than the distance to the margin for class 1. So we would predict class 3. Right. And then the other approach is to consider all possible pairings of classifiers and basically look at the majority vote or the weighted majority vote. So we would try to classify, is it class 1 or class 2, class 2 or class 3, or class 1 or class 3. And then let's say we plug in a new data point, and here it says, oh, I think it's 1, I think it's class 3, I think it's class 1. So out of these, the majority is 1, so we predict 1. Yeah, so depending on your setting, one of these might be appropriate. This approach, the second approach, might not be scalable. If you have a large number of classes, you need to train C choose 2 classifiers, which might be computationally infeasible. While in this case, we only the number of classifier only scales linearly with the number of classes. Okay, so finally, let's just summarize what we've talked about in these 3 videos so far on support vector machines and kernels. We saw that support vector machines are just binary linear classifiers, which where the whole idea is to find a separating hyperplane which has the maximum possible margin. It leads to the maximum possible gap between 2 classes. And this motivation for using the maximum margin is actually rigorously motivated by statistical learning theory. We also saw that if you write down the optimization problem, which is associated with SVM, this is a convex constraint optimization problem, which means that we can actually solve it and find the globally optimal solution. In particular, we used the dual formulation using Lagrange multipliers, where the dual problem turns out to be a quadratic programming problem, which we can solve it very efficiently, and there are many libraries for solving such problems. First, we talked about the hard margin SVM, which can only be applied when the data is linearly separable, but because this is not always the case, we introduced the soft margin SVM, which added slack variables, and this helped us to deal with noisy data. And for the soft margin SVM, we saw that we had this additional parameter C, the penalty parameter C, where we trade off how much we are penalizing the violation of the margin. This linear soft margin SVM can be reformulated as a hinge loss formulation, which can be solved directly using gradient descent because the parameters are unconstrained. In the kernel, in this video on kernels, we discussed that we can move beyond linear decision boundaries and obtain non-linear decision boundaries by using the so-called Kernel Trick, which is equivalent to performing a dot product in some potentially infinite dimensional feature space. And this kernel trick only works in the dual formulation because the dot product xi transpose xj is exactly only showing up in the dual.